Okay. The dreaded trig identities. We've written 3. There's actually a whole bunch of them. We're going to go on a limb and just say that these are the 3 that you're working with, and they've given us a question. So we'll talk about some of the ideas with trig identities. We'll refer to this as the left side of the equation is equal to the right side of the equation. And what you're trying to do is prove this to be true. So at some point, you either want to make the right side of the equation whatever's on the left. So we want to make this sine squared theta divided by 1 minus cos theta. Or we want to make the left side equal to what was on the right, which is our 1 plus cos theta. So essentially, you really work with one side of the equation. That's like a final answer, though. It doesn't mean you can't move a bunch of stuff around. Like one of my first instincts is to get rid of fraction. Take this denominator, bring it over here, carry it out, see what it equals. But when you do a final answer to do a proof, you usually just work on one side and show that this left side at the very end is equal to the right or vice versa. Okay. But all of our rough work, we can move things around algebraically. There's nothing wrong with that. The other thing about them is these are your identities. So you have 1, 2, 3, 4, 5 that they've given you. Each of these identities we can make more identities from. For instance, this tan one, I can say tan theta is equal to sine theta over cos theta. Or if I bring cos over, I can get cos theta times tan theta equals sine theta. So what we just did there is we had tan was equal to something. I've now said sine is equal to something. Or I can leave cos equal to something by bringing tan over. Sorry, I shouldn't go on top. It looks like it's division. It should be cos theta is actually equal to sine theta over tan theta. Just made 3 identities from that. Okay? Let's go to your specific question. Okay, I'm looking at this, and one of the first things I realize is I have a cos, and I have a sine. Might be helpful to get everything in cos if I can. So do I have any identities with sine? Yeah, I got this one that has a cos. I just made one over here. But tan's also involved. This one here has a squared, though. So this one says 1 is equal to something. Can I rearrange it? And it turns out I can. Let's move this over. If I bring cos squared to the other side, I'm left with sine squared theta is equal to 1 minus cos squared. We're running out of room. Cos squared theta. Okay? And then with that same identity, I could have moved sine over, and I could have had cos squared theta is equal to 1 minus sine squared theta. So again, lots of extra identities we've made. Let's go back and work on this one. So we have sine squared theta over 1 minus cos theta equals 1 plus cos theta. All right. We said we want to change the sine theta. We're going to take this sine theta, and what we're going to do is we're going to replace it with this. So essentially, we're going to replace all of this with this. And that's what an equal sign means. These are interchangeable. It doesn't matter the difference. So we're going to plug that in, and we'll get 1 minus cos squared theta. Okay, so we plug that in. We'll leave the rest. 1 minus cos theta. Oh, that's close. 1 plus cos theta. I'm looking at this. It's very tempting to say, oh, I can just cancel one of these out, but I can't. This is squared. This is a singular. So at this point, everything is cos. So we can probably use a let statement. It might simplify things for us. You might say let C equal, and sometimes you'll commonly do it. Let's say let C equal cos theta. And the reason I'm going to do that, I'm going to write it in black now, is 1 minus C squared over 1 minus C is equal to 1 plus C. This might be easier to look at if this trigonometry with all of these different cos functions and sine functions are confusing. We just write it as a single variable. It might look easier in terms of our algebra. Now, this is a little tricky. I have to realize that this can be factored. This is actually a difference of squares. 1 is a unique square. I can square root 1 and still get 1, and I can square root C. So I remember back to some of my old quadratic rules. I have 1 minus C squared. This is a difference of squares, so this can get factored into 1 plus C, 1 minus C. Okay? Just like this idea, 1 minus x squared could be 1 plus x, 1 minus x. We're just using C instead. And if you want to prove that, you can distribute this, and you'd end up with 1 minus c, and this becomes plus c minus c squared. These two cancel out and you get 1 minus c squared. So there's our proof that it works back. So I'm going to factor this, and the reason I'm going to factor that is because I noticed that I'm going to be able to do some canceling after that. So when I factor this, I get 1 plus c, like we said, and 1 minus c, all divided by what was originally in the denominator, which was our 1 minus c, which is still all equal to 1 plus c. Now if we take a look here, these essentially create a 1. When I divide them, we get 1, and I end up with 1 plus c is equal to 1 plus c. And that's my proof. The two things are equal. I should use my let statement one more time. Let's change it all back just so I have a true proof here. Cos theta. So in the end, we end up with 1 plus cos theta is equal to 1 plus cos theta. But algebraically, we essentially prove this.
How would you know to factor?
Yeah, that comes from some experience of looking at quadratics. To know to do that is not something like, if this happens, you must do it. Because there's all different types of factoring. If you have something that's squared, consider that this is algebraically has a similar to a quadratic relationship, and you might be able to factor. Just like you can common factor. I could have tried to common factor out something here. I noticed from lots of experience of doing these that this is a difference of squares. It's not going to be intuitive to you right off the bat. You probably won't see that. But just keep in mind, if I have a squared, there might be some factoring involved in this question. Or I'm dealing with Pythagorean identities, this kind of idea up here.